So today we're going to be talking about IP transports. There isn't any going to be any hands-on labs this class. I mentioned I'm on vacay. I just got out of the literally just got out of the pool for this. So yeah, we're going to have a chill day. That way everybody kind of gets to come along with me on vacation. You get to just kind of hang out and listen, make life a whole lot easier. This is going to be a quick review of like IP and IP communications in general. It is not designed to be a complete guide by any stretch of the imagination. I just want to make sure that I give you enough that we all kind of get on the same page. I'm going to skip some of the common stuff like ports, but I want to, go a little bit deeper than that. If you do want to deep dive on this type of thing, I do cover it in greater detail in the Getting Started in Packet Decoding class. That's a pay what you can class through Antisyphon. I think it's like $25 or something like that. And the next one is in May, and I've done a big rewrite for May. Yay! So that one should be fun. So just as a reminder, we look when we look at this stuff, we tend to look at it in ASCII, right? We're looking at like the IP addresses and the port numbers and some of the different field values. But it's important to remember that all this stuff is being transmitted in binary. We use binary overwhelmingly for a majority of our communications, just because it is very resistant to errors, right? With analog, you can have a fairly high error rate that can slow down transmissions even more. Digitals tend to be a little bit more cumbersome, but because we're getting get rid of the error rates, overall, it ends up working a lot more efficiently. And when we're transmitting in binary, everything is always laid out in a certain order. I've seen folks talk about, oh, hey, I once saw this packet that said it was an ICMP packet, but it had a TCP header. No, no, that doesn't happen. That doesn't happen. It can only be one specific transport, and that gets specified within the IP header itself. So all this stuff gets laid out a certain way. I've talked in previous classes about, this is a frame when we include all the layer 2 and up information. This is a packet when we talk about layer 3 and up. We tend to ignore layer 2 a lot just because it's getting stripped off and replaced every time we leave a network. So we tend to refer to, packet decoding and packet this and packet that. And it's all offset measurement. Yeah. So anytime we're talking about how does a receiving system know how to interpret certain data, it's all specified in the RFCs. And it's all a matter of offset measurement. So if I want to know what the protocol field is, if I want to know what transport is running on top of IP, and specifically for a second, I'm going to talk about IPv version 4, any device that sees those ones and zeros coming by is just going to offset through till it gets to the beginning of the IP header. It's going to offset and it's going to read byte 9. It's going to go in and offset to byte 9. And then it's going to read that single byte of information. That's going to be interpreted as decimal, which means it will have a numeric value. And that numeric value gets checked against a table that lists what codes go with what transports. So in other words, if byte 9 within the IP header has a value of 1, it's going to be assumed it's an ICMP header. If it's 6, it's TCP. If it's 17, it's UDP. And, if it's 47, it's GRE. If it's 50, it's encapsulation security protocol. You get the idea. Whatever that number is going to define how the data in the payload section is going to go through and get interpreted. Now, IPv6, as Bill talked about a couple of weeks ago, is a little bit different. IPv6 doesn't have a transport field or what's called a protocol field. It has what's referred to as a next header field. And that's because with IP version 4, one of the things we decided to include was IP options. And IP options can actually change the size of the IP header, right? So if there's no options, the header is a small size. If we start adding in options, that header gets bigger in size. With IPv6, the IP header is a fixed length. It never changes. But we wanted to include some of those options, like record route and that type of thing. So what we did is we changed the protocol field to be the next header field. And now if there's an IP option turned on, like record route, the next header field will point to a header that is specifically for recording record route options. Otherwise, it'll be transport. So with version 4, that protocol field is always going to identify the transport. With IPv6, it might identify the transport. It might identify another header. And then we might need to go look into that header to see, okay, does that reference a second header or a third header? Or is it going to reference the actual transport inside of that at that point there? So ICMP, ICMP to me is deceptively simple. By that I mean it's our smallest header, right? It's 4 bytes in size or 8 bytes in size, depending upon who you talk to. I consider it only 4 bytes in size, just because there's only 4 bytes that are consistent with every single ICMP type code. And it's not really used to transmit data, or it's not supposed to transmit real data. It's just there for like connectivity checking and error reporting and that type of thing. So it has a very simple use case, but it's probably one of the more complex protocols to deal with properly. We still have stateful inspection firewalls that don't know how to handle ICMP properly, which is a real shame, because it doesn't have to be that way. Probably one of the best descriptions I ever heard of this was from Paul Vicks. He's one of the folks that basically designed the internet. He referred to ICMP as the garbage trowel of the internet. And that's kind of it. ICMP works in the background. Nobody really pays attention to it, but if it's not working, things are going to break really quickly. And that's probably a perfect description of ICMP. It supports unicast communications, meaning it can be from one host to another. It can be broadcast based, which means it can be one host to every other host on the network, or it can be multicast based, which is one host to multiple select hosts. So it supports all of those different types of communication. Unlike TCP, which only supports unicast, you're not supposed to ever see TCP broadcasts. Doesn't mean you won't see them. Doesn't mean somebody won't code the stack wrong, or someone might not be messing around with a packet crafting tool like we were talking about last week. But TCP should be unicast only for all intents and purposes. ICMP can be broadcast multicast as well. And firewalls seem to have a real problem with this. So the problem firewalls have, and I'm going to start getting into this next week, right? So I'm dealing with a little bit of a chicken and the egg issue. So I was going to start talking about firewalls this week. And then as I thought about it, I was like, well, I got to give folks a little bit more information on transports. But if I don't communicate with it, or excuse me, if I don't kind of cover the transport stuff, the firewall stuff won't make as much sense. So I kind of ended up kicking it back a little bit, kicking it back a week. And ICMP really is one of the things that firewalls have the most trouble with. Kafka was asking, is unicast enforced by switches and routers only? Good question. So the only thing switches enforce is what MAC address is that going to, and do I have a table entry telling me where that is? So let's say I have a MAC address of 1234. If the switches learn that the MAC address 1234 is off of port 2, anything going to that MAC address is going to end up going to that port number. If it doesn't know where the MAC address is, or if it's going to the broadcast address, meaning it's all set to all Fs, that goes out every single switch port. So in that case there, let's say I sent a TCP packet to the broadcast address, a switch isn't going to pay any attention to the fact that, whoa, wait, TCP doesn't broadcast. This doesn't make any sense. No, the switch is going to look and say, oh, that's going to FFFFFFFF. Send it out to everybody, no problem. So switches don't get into like the protocol enforcement end. As far as routers go, routers have, routers deal with layer 3 information. So is it going to the local network, or is it going off to a remote network someplace? So routers will get involved at that point there. And whether we'll get passed outside of the network or not depends on what that destination network address is. Okay. Hopefully that clarifies that a little bit. So like I said, ICMP, 2 main purposes: some relative connectivity checking and the ability to go in and do error reporting. And error reporting tends to be what we use it for the most. So ICMP is responsible for things like host unreachable, right? I'm trying to get to a host on a remote network, but that host is offline right now. So the upstream router is going to send me back a host unreachable saying, hey, you can't get there from here. That host isn't around. It'll report things like time exceeded in transit. So if that TTL value that gets decremented every time we cross a router drops to 1, the router, after it has been dropped to 1, knows it can't drop it to 0, and it'll report back an ICMP, time exceeded in transit. Well, the problem we have with firewalls is that if I have a packet leave, right? Let's say I have a TCP packet headed out someplace to the internet. It's going to have a source port, a destination port, a source IP address, destination IP address. And it's relatively easy for the firewall to look at that and say, okay, any combination of those two is okay to go by. So if I now see the source has been changed to the destination for the IP import, and the same thing on the other side, well, that's just a reply and that's okay, and I can let that go through. So when you deal with TCP and UDP, firewalls can just kind of look at ports and look at IPs and make some decent decisions based off of that. But ICMP throws a monkey wrench into the whole thing, right? Like I talked about, the host unreachable is reported by the upstream router. So my firewall might see me go to TCP port 80 on a remote IP address, but now I have an ICMP error packet coming from some IP no one's ever talked to. Is that something that can be let through or not? And some firewalls struggle with that. And we'll talk more deeply about why next week. I'll get into it a little bit this week, but yeah, I'll get into it even deeper next week. And this is where like deep packet, well, it's called deep packet inspection. Really, that's just a relabeling or marketing term for stateful inspection. But stateful inspection is designed to go through and kind of help with those types of problems. But here's an example of an ICMP error. So I know the screen looks a little busy. Follow along with me here. So see the little left-hand red bracket here and the right-hand red bracket? That's showing a decode of the ICMP header that is exposed on the outside of my packet. So this is an IP packet. It's identifying that it's an ICMP packet. So byte 9 is going to be set to 1. It's going to say it's an ICMP packet. And this is set to administratively prohibited. So in other words, the device that's responding here, right, this 24.220.6.168 is saying, hey, I've been told not to let packets through to the IP port or combination thereof that you're trying to access. So I'm telling you, you can't get there because I'm not letting you get there. The host might be up, it might be down. You have no way of knowing. I'm not going to let you get there. So this is an ICMP error that says you're trying to access a resource that that you're being prevented from accessing. Now, if we just look at this outside here, right? How does the receiving system know what's been prohibited? Because this is coming back not from the system that they were trying to talk to, but some intermediary host that says, I have filter rules in place saying I can't let this through. Chris, isn't stateful inspection more about the three-way handshake as opposed to UDP? So stateful inspection really is about how deeply into the packet can we pattern match, regardless of whether it's TCP, ICMP, UDP, or whatever the case may be. It's a little, so I think where Kafka, where you're going with that is TCP is a little easier to firewall because TCP, and we talked about this, we'll talk about this in a little bit, has flags that signify where it is in that communication session. If SYN is turned on by itself, we know that's the first packet in the session. So it's easy for me to implement a rule to say, don't let through connection establishment, but let through replies. With UDP, it's harder because there's no flags identifying where I am in the communication session. So when I see a packet go by, I don't necessarily know just by decoding the packet itself, is this an initial query or is this a response? I got to go a little bit deeper to deal with that. And I'll get into that a little bit more as we go through. And looks like somebody at the club. Yeah, Eric's got a great description of stateful inspection as well. Thanks, dude. So yeah, but this is my outside header. And like I said, it's coming from an intermediary host. So I have no way of knowing what is this associated with. So what ICMP does to fix this is it embeds the original packet inside of the payload. And that's shown inside of these blue areas here, right? So down here, you can see the red, and then you can see the blue. That just kind of correlates with up here. See this 4,500? That's kind of a good value to look for in hex when you're looking at packets, because it's the start of an IP header. It means that it's IP version 4. The packet is 5 32-bit words or 20 bytes in size, and type of service has not been turned on because nobody uses it. That's pretty common for most IP packets. And if you ever offset into a packet and you see 4,500 again, it's worth digging a little bit deeper to say, hey, is this an IP packet buried inside of an IP packet? And that's in fact what we have here. So it's inside of the blue this is the packet that caused this administratively prohibited to get triggered, right? This is the packet that I was trying to send to 8.26.204.25, that 8.220.6.168 said, sorry, can't get there from here. So you get the idea. So with ICMP errors, the way we track what caused this error to take place is we take the packet that was in error embedded inside the body of the payload, up to a total of 60 bytes in size. So I don't get the entire original packet, but I'm going to have 60 bytes total, which is plenty to be able to look at. That's going to give me my IP header and enough of my TCP header to be able to see, yeah, this is in fact, what caused this error to go through and take place. So stateful inspection, decode the blue section and compare it to the state table. So what do I mean by that? I mean that, so this ICMP error comes in, and as we said, it came in from an unknown host. How do we know if it's okay to let this through? Well, what our firewall needs to be able to do is say, that's an ICMP error. I won't necessarily see a response coming back from someone that one of my internal hosts tried to talk to. I need to offset into the payload. I need to decode this because this is the IP header and the original transport header of the packet that caused this error to take place. And I need to use that information to go match against my state table. So again, in this case here, I had a system that was trying to get to a DNS server, and it's not allowed to talk to that DNS server. So that's why this system kicked back and said administratively prohibited. You can't get there from here. So how do I know which of my packets caused this admin to take place? Well, I can find that information right within the payload here. And as I said, ICMP is not designed to transmit data, but you can certainly transmit data inside of it. The first command and control channel that I ever ran across was based on ICMP error packets. It was actually kind of wild the way it happened. This was right around circa 2000, right? So it was, Y2K, the whole world's going to end. It was when all that stuff was going on. I got pulled in as part of a group to provide security and tech support within the government to be able to look at things to say, hey, does this look like a Y2K thing? Or does this look like somebody trying to do evil and make it look like it might just be a Y2K thing? Which is it? So I was with a group of people, that would go through and review this stuff. So we'd have people submit stuff in. And we had this ICMP error packet that was being broadcast to the .0 address, which was the network address of the network that it was being sent to. And the person who saw it sent it to us and said, this looks, hey, seeing this packet, and it repeats every now and then. It looks kind of weird. Don't know where it's coming from. Don't know what's going on. Check it out. And of course, what's wrong with that is an ICMP error is a response to a host that is having problems communicating. So why is it going to the network address, right? The network doesn't send traffic. .0 never transmits. So why is it going to the network address? And I was working with a few people that pulled some lame excuse out of their backside and closed the ticket. And I looked at it and I'm looking at it and I'm like, That's just not making sense. And we were supposed to like get tickets closed as quickly as possible because, hey, that's what sport people are supposed to do, right? And I kept pissing people off because I kept opening the ticket back up. Nope, that example you gave or that reasoning you gave makes absolutely no sense at all. We need to open this back up again. Long story short, go back to the early days of internet communication, and BSD systems used .0 as their broadcast address and 255, as their network address, assuming a Class C subnet, right? Really, what I'm saying is, the all the low order bits turned off was broadcast. All the low order bits turned high was network with BSD. But System 5 was the other way around. .0 was network. .255 is broadcast. And we said, hey, they're both Unix systems. They should be able to talk to each other. We need to fix this. And, they flipped a coin, or however it went. They decided, okay, 0 will be network and 255 will be broadcast going forward for all systems, which meant BSD was doing it the wrong way around. And what Sun said was, okay, fine, we will accommodate that. But for backwards compatibility, since no one should be sending to the network address anyway, we're going to continue to rationalize that as being a potential broadcast in older Sun OS systems. And what was getting compromised was Sun OS systems. So this was a real crafty way to send marching orders to a system that didn't let you see what the system was, right? If there's a command and control channel going to 192.168.1.10, hey, which system got compromised? That's pretty easy, right? 192.168.1.10. That's the one doing the C2 session. But these were going to a network address, which meant it could be any Sun OS system on the network. And if there's a couple dozen or a couple hundred, good luck figuring it out. You may not necessarily be able to figure it out quickly. So what looked like a rogue ICMP error turned out to be the first command and control channel I ever found. God, was that really 25 years ago? Yeah, that was 25 years ago. That's how long we've been dealing with this crap flaw. So yes, you can in fact embed data inside of ICMP packets. So changing gears a little bit, we got UDP. So this came up a little bit from like a firewall perspective as well. UDP is lightweight. It is designed for the bare minimum needed to try and transmit data from point A to point B, right? So we've got some port numbers here. We've got a CRC check. We've got a length field, and that's it, because that's like the bare minimum you need to get data from point A to point B. Connectionless, no concept of state. I said TCP is very formal, right? So think of TCP as being similar to me walking in the room. Hi, I'm Chris. What's your name? Oh, hey, I'm Steve. Nice to meet you, Chris. Nice to meet you, Steve. Are you having a good day? Yes, you are. Okay, great. Here's data I want to transmit to you now, right? That's a TCP conversation. With UDP, I might walk in and say, hey, where's that code I asked for? And say nothing else, right? That's UDP. Just straight to it. You don't even bother trying to establish a communication session first. I'm not even, at least by like shaking hands and greeting someone, I know I have their attention. With UDP, you don't get that, right? Like maybe you have their attention, maybe you don't, type of thing. So UDP is designed to be the bare minimum you need to transmit data from point A to point B. So you'll hear TCP referred to as reliable and UDP referred to as unreliable. This is one of the reasons why UDP doesn't do connection establishment. UDP also doesn't have any error correction built into it. So that's why most of our protocols today are built on TCP. Now, here's the problem. TCP was written back in 1982, or early 80s anyway. It's been in use since about 82. Longer than I'm guessing a lot of people who are on this webcast have actually been on this planet for. So you won't remember what the internet was like back then, right? The internet back then was, a high-speed internet connection was like 300 baud. And, if that dropped 50 times a day, that's what we called stable, because it was only you could get it a half hour worth of use out of it before the network went down. That was considered stable back then. So TCP was written to be stable in those types of conditions. We don't have those types of conditions anymore. So UDP tends to be a little bit more preferable. We'll talk about the QUIC protocol that gets used a lot these days. That's based on UDP because we don't need all that reliability that's built into TCP. Well, wait, Chris, does that mean that you can lose transmissions and it's not reliable? You can't count on it? Not necessarily. I can build that. I can build in reliability at the application layer. It doesn't have to be done at the transport. It's a laziness thing, right? If I use TCP, I don't have to worry about reliability. The protocol's already doing it for me. If I use UDP, well, now I have to build in some level of reliability at my application layer. UDP also supports unicast, broadcast, and multicast, just like we talked about with ICMP. The other thing that's kind of interesting about UDP is that it can be bidirectional or unidirectional. So for example, what we're looking at here is a system sending log entries to a logging server. So when I send my logs to a remote server, if I'm using UDP 514, no response back means they got that log okay. Oh, no, it doesn't make sense, right? That's like, me saying something to someone in a crowded room. And if I don't hear anything back from them, well, they heard what I had to say, no problem. Well, you can't necessarily count on that, right? The thought process is if that system didn't get the packet because it was too many hops away, you'll get an ICMP error. If the port's closed, you'll get an ICMP error. So UDP is really relying on, hey, for most things that might go wrong, I'll get I'll get back an ICMP error to let me know something went wrong, and I can take action to it accordingly. If I don't get anything back, I'll just assume it made it through. No, it's not always how it works, right? What if I have a firewall in the way with a drop rule? Well, the firewall will drop this packet. No response will get sent back to the transmitting source. So the transmitting source will think these log entries are getting through when in fact they're not. And that's not a good thing. So they can be unidirectional. All my traffic is in one direction and one direction only. Syslog's a great example of that. Or it can be bidirectional. DNS is a good example of that. So I'll use UDP 53 to send a DNS query to a system, and then it will send a response to that query. So for example, I have a system here asking a DNS server, hey, I need the A record, or I need the IP address of config.teams.microsoft.com. And then here is my response coming back. So I got 3 records back, and it's telling me that is a C name, meaning, hey, that host name is associated with these 2 hosts as well. The A record for it is this IP address right here. So ask a question, get back an answer. UDP can be bidirectional as well at the same time. Let's see. Also, Internet Explorer was classified as munitions, but that's another story. Yeah, that goes way back. Back when, should we let things be more than 56? Should we let people use encryption with bigger than 56-bit keys? It goes back to those days. Really, where that law came from was back in World War II, right? So we're talking the 40s. Your average person did not encrypt their communications. There was no reason to. But as time went on, it became easier to eavesdrop, and therefore the need for privacy went up. So people wanted to start encrypting their communications, especially over the internet. And they kind of tripped over that munitions law, which was, hey, if you're encrypting data, you must be up to no good. Therefore, it's illegal. And, that goes back to worrying about spies. So, they've had to kind of modify the laws around that as time has gone on. Let's see. Isn't UDP a problem with IDS IPS because of dead time then, i.e. no detection alerts? So there's kind of 2 ways to look at it with IDS IPS. It could be detection of events taking place on the wire, right? Like the IDS. So IDS IPS is intrusion detection. And one is just detecting, the other one tries to do something to stop attacks if they take place, which don't work most of the time, but that's another story for another day. But one of the problems you can run into is that I might have the data that would normally get detected if it was all inside of a single packet spread out over multiple packets. And some IDS systems may be able to consolidate all that data and then do the pattern matching. Some of them may not. And for the ones that don't, they're not going to be able to go in and do a detection on that. So yeah, Kafka, I would absolutely agree that when you're talking about IDS, UDP, if it's spread out and that isn't getting reconstrued back into its original datagram first, you're absolutely going to miss things. As far as it doing error reporting, yeah, you could run into the same type of problem where you're sending your alerts, via UDP 514, and they may not be making it through. That's fairly easy to solve today, though, because most logging servers also support TCP. And then there's another port up in, I think it's like the 500 range, where you can actually encrypt those log entries as they get submitted as well. Let's see. Yeah, the 128-bit version back in the day. Yeah, I had fun at the border one time when I had a customs official asking if I had any 128-bit encryption on my laptop. Luckily, I could dual boot into Linux with a guest account, and they didn't know what to do when they moved around the mouse and couldn't get a mouse character or couldn't get a little mouse pointer. So that was fun. That was the only thing that kept me out of jail that night. That used to be more of a thing then than it was now. And yeah, there's a lot of things that went on with Zimmerman and Snyder back in the day. Cool. So yeah, UDPs and firewalls. One of the biggest problems you can have, or we used to have, was that DNS used to use a fixed source port of 53 between servers. So the source port would be 53, the destination port would be 53, and they had to change the DNS software to and the RFCs to kind of fix that one. If we're talking modern DNS with a decent stateful firewall, handling DNS queries should be no big deal, right? Those are fairly easy to go through and take care of. Usually no stateful inspection implemented. What do I mean by that? I mean that we don't necessarily go in and look to see what type of DNS queries are taking place and make a decision based on that. We just kind of decide, hey, do I want to let UDP 53 to the server or not? Yes or no. And if I don't want to let it in because it's an internal resolver, I don't want people out on the internet doing it, most modern firewalls are going to be able to deal with that pretty easily. I talked about IDS, IPS with UDP if I spread it out over multiple packets. One of the things you kind of run into with UDP is that you don't really know when it's done, right? With TCP, we have it what's called referred to as a FINAC exchange. So the idea is I'm done sending you data, so I turn on certain flags to signal to you I'm done sending you data. And then when you're done sending me data, you turn on those same flags, and now we know the conversation is over. So it not only has a formal start, but has a formal way of ending as well. UDP doesn't have that formality. So I see a UDP packet go by. Is it just the one packet, or is it going to be multiple? So most tools hedge their bets. What they do is they say, hey, if I see a UDP packet go by and another one goes by within 30 seconds or less, I will consider that to be part of the same session. Well, we don't really have sessions with UDP, though. So technically, that's not correct. But if I want to have some ability to pick up on patterns when they're spread out over multiple packets, I need some level of timing to be able to say, hey, how long do I wait to see if more data shows up so I can try and combine it with this data versus, this must be a new transmission that's taking place. 30 seconds tends to be the default for most intrusion detection systems and most firewalls that are out there today when we're talking about UDP. Then we get into TCP. And TCP is the one that most folks are more accustomed to. More overhead than UDP. Yeah, the header is bigger. So UDP, the header is 8 bytes in size. TCP, the header is anywhere from 20 bytes to 60 bytes. So it can grow fairly large. That it doesn't sound like much, but when you're talking about overhead in every single packet, that's 40 bytes in every packet that could have been data. And now it can't be because we're using that space to transmit header information instead. So that's what we mean by more overhead. We also talked about, there's that 3-packet formal handshake that needs to take place before I start sending data. That's overhead, right? Anytime we're throwing packets on the wire or we're throwing stuff in the headers that doesn't need to be there specifically to transmit data, that's overhead. And the more overhead we have, the less room we have left over to be able to actually transmit data. Connection oriented, meaning state is maintained. Yeah, we talked about that. And I'll get into a little bit more when we talk about flags. Has built-in error reporting. Yeah, TCP has the ability to figure out when packets go missing. Well, technically, it's when data goes missing. It doesn't look at it as a packet or 2 packets went missing. It just knows, hey, I'm missing a chunk of data here, right? I'm missing 232 bytes right at this spot here. It doesn't know if that 232 bytes was transmitted in 1 packet or 5, and it doesn't care. It just knows this chunk is missing. This needs to get retransmitted. UDP doesn't have any ability to recover and figure out when data goes missing like that. Has built-in error reporting. So I mentioned that if I try to talk to a UDP port and that UDP port is closed, I'll get back an ICMP error. Well, TCP has that error built right in. It's called reset flag. So if I try to talk to, let's say, TCP port 80, and there's no web server listening, I'll get back a TCP reset ACK packet. Hey, sorry, there's nothing listening on that port for you to be able to talk to. So the error reporting is built right in. Also has built-in flow control. So what flow control means is that, let's say I'm talking to a web server, and that web server is really busy because there's lots of other people talking to it. If I try to send it data too quickly, and it fills its buffer. When a buffer gets filled, typically the only option is to throw stuff away. Anytime you start throwing stuff away, now it takes time to recover from that happening. So we want to avoid throwing data away as much as we possibly can. So what flow control does is it gives that server a way to communicate back to me and say, hey, you need to send me data slower. And really what it's going to do is it's going to come back and say, hey, you can only send me 500 bytes of data before you need to stop and wait for me to acknowledge the proper receipt of that data before you then again send me another 500 bytes of data. And if that goes well and things are working fine, I may kick that up to 600 bytes and 700 bytes and so on. If we start running into problems, I may make that number smaller. So flow control allows one system to control the flow rate of data that's being received from another system. We talked about this, TCP unicast communications only. Because of that formal handshake, right? Like if I send a SYN packet to the broadcast address, if I start getting SYNACs from a bunch of systems back, it's going to get really complicated to try and set up those connections with all those systems at the same time. Doesn't make a whole lot of sense. So TCP is specifically designed to only do unicast communications. Now, with that said, I've crafted some SYN packets to the broadcast address on occasion and been surprised by the systems that respond back to that. It can happen, but that is a coding error that's not a natural effect of what's been written into the RFCs. And here's the TCP header. Much bigger, much more complex. The other thing that's different about the TCP header, it has options to it. And the options can make that header grow in size. So with my UDP ICMP, most of my headers, they're a fixed length. They're always going to be the same size. TCP can be as small as 20 bytes. Like we said, it can grow from there. It can go up as large as 64. Now, I get into this more when I get into like packet decoding, but the IP header, it's actually pretty rare to see someone turn on IP options. And if you see IP options turned on in a packet, more than likely somebody's up to no good. More than likely somebody's doing something they shouldn't be. It's not, 99% of the time. There's that 1% of the time that there might be a legitimate use case for using IP options. But today in a modern network, most of the time you don't need to use them. TCP, it's the complete opposite. With TCP, it's more common to see options turned on in every modern day operating system. If you don't see options being used, that's usually an indication somebody's doing some packet crafting, right? They're crafting a packet where they wanted to set a few values. They didn't worry about the TCP values because they don't really care about a good communication session. So that's why no TCP options were turned on in that session. The other caveat is that with the exception of one TCP option, timestamp, all the other options only take place in the initial packet of the session. So it's either in the SYN packet or the SYN-ACK packet. Those options don't get indicated after that. Timestamp is the only one that's different from that. C. Branton, how does the MTU relate to packet size? If those packets are much smaller, expansion when required, or data transfer, or is it just max packet size? So good question. So MTU, maximum transfer unit, is different in that that describes how big of a frame we can have at layer 2. Right. So for most Ethernet networks, it's going to be around 1,500 bytes. It might be 1480. It depends. It's going to change whether we're doing VLAN tagging and stuff like that. But for the sake of argument, let's just call it's around 1,500 bytes in size. When we talk about window size, how much data can be sent before you need to stop and wait for an acknowledgement before you start sending data again, figuring out what to use as a value once we're into the communication session is pretty easy, because the system on the other side is going to say, hey, let's speed up, hey, let's slow down, let's speed up, let's slow down, based on how it's responding. But I got to pick something to start with. And what a lot of operating systems do is they just kind of like a back of the napkin calculation. They say about 4 or 5 times the MTU. So the MTU kind of plays a part in the TCP window size based on that off the back of the napkin calculation. But not everybody follows that. Linux actually starts off with a much bigger window size than that, just because it knows it can. So with that said, that MTU restricts the size of how big the frame can be, which in turn limits the size of how big the packets can be in size of that. So one of the things we have for a TCP option is a negotiation referred to as maximum segment size, MSS. And the idea is, hey, I'm going to tell you what my MTU is, and you tell me what your MTU is, and we'll both make sure that when we send data, it fits inside of that. The thought process being that a small MTU is most likely to be at one end or the other of the network. Now, with that said, my experience has been it shows up in the middle a lot. Sometimes you end up over these, you'll end up going over like an older frame relay link, right? Frame relay still gets used, and frame relay supports a smaller MTU size. So that's not going to help. So I think it's, so maximum segment size, which is one of the TCP options, tries to help solve some of that, but it doesn't do the best job of it. So those are the ways the MTU kind of relates to TCP communications and TCP options, in case that's helpful. Good question, though. Good question. So yeah, like I said, the TCP header can grow in size if the options are set. With TCP, modern day, most operating systems will use one or more TCP options, but it usually only gets negotiated in the first packet of the session. Now, our TCP flags are how we identify state. It's the 6 low order bits in byte 13 of the TCP header. So if we go back here a little bit, here's our flags, right? But my flags are only from here over. I have 2 bits here that I'm not using for flags. Those get used for ECN, explicit congestion notification, which tends not to get used. ECN is kind of a way. So we talked about flow control lets the endpoints control how quickly data gets sent back and forth between them, right? Well, they're not the only 2 systems involved in the negotiation session. There might be 15 routers that are in the middle of that session, those sessions as well, and they need to handle those packets too. What if one of those routers starts getting overloaded? Well, historically, the only option was for the router to start throwing stuff away. What ECN tries to do is it tries to be a method of giving the router the ability to reach out to the endpoints to say, hey, you need to, even though the other side is doing just fine, you need to close up your window size because a router between you and that endpoint is about to roll over and start throwing away packets because it's running out of buffer space. Now, I think the thought process is, well, let other people use ECN. My data is important. I want to let it go through. Right? That's why we tend to not use ECN. But, it's there. But yeah, those 6 bits are used to identify different portions of the communication session. I'm going to kind of flip around a little bit on these to do, because I kind of listed them out in the order of the bits, but I want to kind of talk through them in the order that they actually get used. So SYN flag turned on by itself, that's how I start a session. So when a system turns on the SYN flag and all the other TCP flags are turned off, that's its way of saying, hey, I'm trying to start a new session with you. We may not have been communicating with each other yet. We certainly haven't been communicating as part of this specific communication session. This is a brand new session I want to start up and talk to you with. The acknowledgement flag is a way of acknowledging receipt of data from the system on the other side. One of the interesting things about the acknowledgement flag, it's turned on all the time. There's only 2 conditions I'm aware of where you won't see the acknowledgement flag turned on. One is when the SYN flag gets sent, right? Because SYN's the only thing turned on. ACK is off. So starting a brand new session, that's one case where ACK won't be turned on. The other time I've seen it is if I send a TCP packet with the acknowledgement flag turned on to a closed TCP port, meaning there was no session. There should never be a packet with just the acknowledgement flag turned on being sent to it. Somebody's crafted something. In that case, many operating systems will return just the reset flag turned on, and that's it. Those are the only 2 times I've seen it. Outside of that, every packet you see go by should have the acknowledgement flag turned on. When the session gets done, we have the FIN flag that gets used. So if I send you data, I'll send you a FIN-ACK. And then when you're done sending me data, you send me a FIN-ACK. And then we each acknowledge the FIN-ACK sent by the other side. Once that happens, that session is considered closed. Now, what if something goes wrong? What if, let's say, your system loses power? And I'm trying to communicate with you and you can't respond because you're offline. Well, I don't want my session to stay, we don't want the session to hang out there forever. So my systems need some way to close the session with you that doesn't involve using FIN-ACK packets because you're no longer responding. And that method is to send a reset. A reset means, hey, something's gone horribly wrong with this session. I don't see it as being recoverable. You're not responding to me anymore. So, yep, this session's kind of dead now. So reset, consider it a dead session. The other flags you might see is the push flag. So the push flag, data gets handled in chunks, right? So we're sending these packets that are about 1,500 bytes in size. Less once you take off the Ethernet headers. It's more like 1480 on average. 1460, 1480 bytes is about what you're going to see for the average packet size. And some of that is going to be IP and TCP header. So I've got even less than that for a data chunk to work with, right? So we're talking less than 2K. Less than 2K is getting sent in every packet. Well, if my computer needs to interrupt and process 2K all the way up to the application layer every single time a packet gets received, that's going to chew up a lot of free cycles, right? It's going to make trying to use the network very processor intensive. So what we do is we buffer it. And the default is like 8K. So it's not like you need a lot of packets to fill that buffer because it's only 8K in size. But it's also, we're interrupting 1/6 as many times as we would if we did it for every single packet, or possibly more. So there's like an 8K buffer that gets filled up, and then that gets sent through the stack. The push flag is designed to say, hey, this is the end of the data stream. If this doesn't fill that 8K buffer on your side, you need to push it up the stack anyway, because there won't be any other data showing up after this. You'll see the push flag get used a lot with SSH, right? If you watch an SSH session, try this sometime. Launch a packet sniffer, run an SSH session, and then just type commands. SSH, every time you hit a key on the keyboard, sends that key to the other side. So you're sending one key. Well, that's not a K worth of data. That won't get read by the other side. So what you'll notice in an SSH session is the push flag is set all the time. Whereas if you're using a protocol that's designed to move big chunks of data, it's not going to set the push flag until it actually needs it. The urgent flag is used for out-of-band negotiation. So SSH is probably another great example of that, right? Because normally commands get processed FIFO, first in, first out. So if I go in and I type a command that says RM, slash, or sudo RM space slash dash F, force delete the entire drive from this point here, from the root of the drive. If I type in that command and I do it as root, that's going to try and nuke every file that is not currently locked on that system. My operating system is about to go away. Well, if you've ever accidentally started deleting stuff and then used the Control-C command to kill it, you've used the urgent flag. The urgent flag is a way for me to send data to a system and say, hey, I know I've been sending you commands, but interrupt that for a moment and process this immediately. Because without the urgent flag, Control-C would never work. When you'd hit Control-C, that wouldn't get implemented or that wouldn't occur until after the application finished, which kind of takes away the use of using Control-C, right? So that's when you may see the urgent flag getting used. I'll get into this a little bit more, but TCP is a lot easier to firewall because I can basically say, hey, if SYN is turned on by itself, that's a new connection. If SYN is not turned on by itself, then it's not a new connection. It's part of an established session. So if I'm worried about people doing brand new inbound connections, but I want to let through replies for data, I might say, hey, if SYN is equal to 1, and that's the only thing turned on for TCP flags, don't let it through. But all other flag combinations are okay. Well, I'll get into this again when we get into firewalls. But we actually looked at this last week when we did packet crafting. We talked about how some operating systems like Linux, if you turn the FIN flag on by itself, it'll issue back a reset if that port's closed, but it won't respond if that port's open. Well, if I'm letting through anything that doesn't have SYN turned on by itself, I'm going to let through those FIN flags. So a static filter is going to have problems protecting systems from a FIN scan, which is not good. Not something we want to see. So again, I'll get into this a little bit deeper when we get into the stateful firewall stuff starting next week. But stateful does allow us much better security with TCP, not just other protocols as well. And again, I'll get into that a little bit deeper as we go through. Originally, what stateful inspection was used for with TCP was for FTP. FTP was this weird protocol we used to use. We don't use it anymore because it sends the credentials in clear text, and that's bad. But FTP had what was referred to as a command channel and a data channel. So the command channel was where you would log in. It's where you would issue your commands. The data channel was where you would actually transmit that file information. So one of the problems you ran into is you could say, hey, let through the command channel, and that'll let you run commands, but you can't actually transfer any files because that's going to use a different set of ports. So stateful inspection was implemented in order to be able to watch FTP sessions and open up the ports needed on the fly in order to accommodate those data transfers. I'll get into this more when we get into like the stateful firewall stuff and stuff like that. But that was like the original use case for it. And when a firewall says it's stateful inspection, it can make that claim if it statefully inspects one single protocol, which means it might be statically handling a majority of the traffic that's trying to go by. But if it inspects that one protocol, they're going to call themselves a stateful inspection firewall. This is why you can have two stateful inspection firewalls, and they will handle different protocols completely differently, some more securely than the other. And I'll get into that as we go through. FTP is still used by most printers, unfortunately. Yeah, yet another reason to stop killing trees, right? Yeah. FTP got to make that go away. Ports 21 and 22. Um, it was actually port 20, if I remember correctly, 21 was the command channel. 20 was the port used if you were using active FTP. The server would create a connection from port 20 to an upper port number on your client, which also caused problems because now the command session is going from client to server, but the file transfer session connection establishment is going from the server to the client. And that might cause firewall problems along the way. Then they implemented FTP passive mode that was from an FTP upper port to an upper port, but that kept connections in the same direction, client to server, and that made life a little bit easier there. And then we have the QUIC protocol. So when you look at, if you kind of do a statistical breakdown of what is the most popular protocols being used on the internet today, one of the top ones are going to be DNS. And that makes sense, right? We type in names, we need IP addresses. DNS is what takes care of that. So you see a lot of DNS traffic taking place on the internet. But if you look at what's the next protocol being used, it's probably HTTPS, right? It used to be HTTP, but we encrypt our sessions to everything now, just in case, like your Google searches. Google will not let you do a clear text search anymore. You got to use HTTPS. If you try to connect to port 80, it's going to redirect you to the secured port. So a majority of the traffic out there is HTTPS, which means it's HTTP traffic that has been secured with TLS. TLS is, I'll get into this when we get into VPNs and stuff like that, but TLS is a protocol, which means it's a suite of algorithms that does a couple of things. It helps to set up a secure channel over an insecure medium. It helps to establish secure communications. And then it comes up with an expedited way to transfer data back and forth while keeping it in a private format and validate that every packet received was actually transmitted by the host that we think it is. If the TLS rolls in an awful lot of security. But it does that using HTTP. And HTTP leverages TCP. And we talked about there's a lot of overhead with all that. So what QUIC is QUIC is HTTPS, but using UDP port 53, or excuse me, UDP port 443. So TCP 443 is HTTPS. QUIC is UDP port 443. And it operates a lot like HTTPS, or it provides the same security services, but it has a different set of protocols for being able to go through and do that. Like what? Well, unfortunately, a lot of the changes that have been made have been in the interest of speed and performance at the trade-off of potential security. So what do I mean by that? Let's see. Kafka was asking, is TLS implemented at app layer or transport layer? Good question. It's actually at the session layer, which is right above the transport layer. So it's actually sandwiched in between those two. So with an HTTPS session, let's say I go talk to a secure website. And then 5 minutes later, I go and connect to that same secure website again. Then 5 minutes after that, I go connect to that secure website. I'm going to establish security each time. I'm going to get that server's digital certificate. I'm going to check the signature on the bottom and make sure that was signed using the public key of the server that issued that digital certificate. I'm going to use the public key that is inside the digital certificate to set up a secure session with that system. And I'm going to go through that every single time. With QUIC actually gives you the ability to say, hey, we already did that. Let's not bother going through it again. And it's done in the interest of performance. Now, yeah, you get better performance because you're not having to go through that negotiation again every single time. But there's a security trade-off with that. There may be things that change that you didn't expect. Now, it's not an easy attack to pull off by any stretch of the imagination, but it's like we've got this big, huge brick wall. right? And we're trying to keep out the bad guys, and we've pulled out a brick. Now you can argue, hey, missing one brick, yeah, the bad guys aren't going to be able to get in. It's only one brick that's missing, but that one brick might make the difference, right? Maybe they use that to peek through to see when we're actually watching. Maybe that's a leverage point to pull additional bricks out. You get the idea. Anytime we kind of weaken security, there's a cost for that. And QUIC kind of does that in a nutshell. And it's still kind of a work in progress. We're still seeing updates for this. And quite honestly, QUIC to me is kind of, I don't want to say this without like getting on my soapbox. Okay, I can't. But I'll keep it quick since we're already at the top of the hour. How we develop RFCs have changed. We used to develop RFCs to make protocols the best we can. That has changed so that companies that can financially benefit from certain protocols being implemented are pushing engineering to get those RFCs generated. A great example, DOT, DNS over TLS, right? That gets pushed as, oh, it's a privacy thing. Your ISP can't, see what your DNS queries are anymore. Yeah, you're right. They can't. But you know who can? The DNS server you're using out on the internet that you're connecting your DOT sessions to. So all that does is move who can steal and sell your data from your ISP to be someone else. It provides no security beyond that. But what it does do is it makes it harder for security people trying to protect a network who are using DNS queries to do that, to actually be able to do their friggin' job. So we're starting to see RFCs come out that are helping companies to monetize business models that weren't initially available to them, but is making our job in security a lot harder. And I think that kind of stinks. So QUIC and firewalls, yeah, you're kind of limited around, I can let through UDP 14 or not. You can't really control a lot of what goes on. One of the things I don't like about QUIC is that you can connect to a server using QUIC, and that server could generate new sessions back to your system. It can do connection establishment as a reverse channel, and that's part of the specification to allow it to do that. Today, with HTTPS, your client needs to start every single one of those sessions. The server can't start something new. It can, it can try and motivate you to do that, but it's still up to your system whether that's going to get created or not. With QUIC, yeah, no, bidirectional. Either end can establish one. Once the secure channel is set up, anyone can initiate new sessions, and that goes out bidirectionally. And haha, it's crypted, so you can't tell which was doing which. I hate it when that happens. So yeah, to me, there's a lot of security concerns here. But like I said, I don't want to spend too much time up on my soapbox over this. So that's our quick talk on transports. Next week, I'm going to talk about firewalls. We'll talk about the difference between static, stateful inspection packet filters. We'll also talk about proxies. We'll talk about the strengths and weaknesses from them from a firewall perspective. So that'll be next week. There'll be no labs next week because the week after will be all labs using firewalls. So for 2 weeks from now, what you'll need is access to a Linux system. And I'm going to give you a bunch of scripts you can run on that Linux system that will quickly set up static, stateful, and stateful inspection firewalls. So we can go through and do some quick security testing to see what's the strengths and weaknesses of each. So that'll be a couple of weeks out. But hey, this is all I have for today. Keith, you got anything else you want to toss in? Keith, you're on mute.
Yeah, it would help if I clicked in the right zone there, but no, I have nothing to add. That was great. Thank you. Yeah, that was really good.
Same here. Nice work, Chris.
Yeah, great subjects. I mean, and I love the engagement on Discord. I mean, we just have such a great community. The threat hunter community is just so cool. So I appreciate everybody. Oh, now I can't hear you, Chris. You're on mute now.
That was weird. Just all of a sudden the system said muted. So I'll blame Bill.
That must
no.
have been me.
It must be HK. He's still hanging in the background. He's like, if I don't turn on my camera, they won't know I'm here. I'll get even with Chris for all the hazing he's been giving me as a new employee. Let me keep putting him on mute. That must be it.
Yeah. Yeah. Well, it's the mute virus. It got me first.
The mute virus. Yes. Awesome.
Hey, also, I'd like to mention that the YouTube live feed for this week totally failed. So our apologies for that. But the YouTube live feed will return next week.
Bummer. Can we get a recording of this put
Yes.
up on YouTube? Awesome.
Yes. Yeah, we'll end up doing that. It's just before, like for our Fireside Fridays archives page, which is at our website, the Fireside Fridays page. Usually I'll add the archive recording the same day, so it'd be there today. But in this case, it may be Monday, Tuesday by the time we get that up there.
Yeah. And I have to come up with a better way to monitor questions on that. Like it's easy when it's your account that posts, but since we post it from the active countermeasures account, I have to respond from my personal account, and I don't always see when comments get posted. So I need like a hacky Bill script or something to go through everything that ACM has posted for videos and see if there's new comments.
Yeah.
There you go.
And as far as the certificates for this session, they should go out today. I mean, I should be able to get those out today. So anyone who's authenticated into the Zoom session will receive a certificate.
Yeah, but hey, give them till Wednesday. Give them till Monday, because let's be chill.
Okay, that works for me.
Cool. All right,
Thanks,
thank you,
guys.
folks.
Yeah.
Appreciate everybody joining in. Thank you for your time. We will catch you next Friday.
Awesome.
Have a good one.
Thanks, Chris. Thanks, everyone.
Bye-bye.